In the last lecture, we saw a strange attractor, namely the Cantor set, which was somehow controlling or governing the chaos game. And in this lecture, we will also continue to look at attractors, but arising from a different dynamical system. So let's review a little bit. What we saw when playing the chaos game, or in our analysis of the chaos game, that no matter how you play it, you find yourself strangely attracted to the Cantor set. That is to say, you're generating a sequence of points which are closer and closer and closer to the Cantor set. And I pointed out that a similar thing happens in the two-dimensional chaos game. There, the Sierpinski gasket is the strange attractor. Now, maybe you get the impression that this can only occur because of the fact that we had the coin tosses. In other words, we had some randomness in the definition of the dynamical system. But in fact, you can also have a strange attractor even in a deterministic dynamical system. That is to say, a dynamical system in which there are no random elements. In fact, we already encountered one. It wasn't mentioned earlier in the course, but in a previous part of the course, we were looking at a dynamical system that has a strange attractor. And that was when we were looking at logistic growth models. So this takes us back to a previous part of the course where we were learning about sequences and recursion. And you'll remember that we looked at three increasingly complicated models. First the linear model, then the exponential model, and finally the one that we're talking about here, the logistic growth model. Over on the right, I'm showing you and reminding you what we had said about the logistic growth model, that it was built on certain assumptions, that these assumptions led us to this rather compact formula, which says that Pn plus 1 is R times C minus Pn times Pn. That is to say, if you want to compute the population 1 unit of time further along, you take the present population and you multiply 3 factors, one of which is the present population, another is the elbow room, and R is a constant which is used in the model, and it's called the growth parameter. So we had already explored that. Let's look again at those same pictures. So in each of these examples, I'll be looking at a logistic growth model, and in each case the carrying capacity will be the same. It will be 1,000 organisms. And also I'll just start with initial population halfway to the capacity, that is to say 500. So always carrying capacity of 1,000 and initial population P0 of 500. And you may remember that you did something very similar, that you worked with a spreadsheet and you examined the various possibilities for the population sequence. And here was one of the examples you looked at. If you use the growth parameter R equals 0.0015, then here's the population sequence that you see. So you see it drops down initially from 500 to a little bit below 400, and then a little bit more, and it's always dropping, but pretty soon you can't see the drops because they're so small. That's because there's a limiting value to the population sequence. It's about 333. Now, another way to say that, using our new language, is that there's a single point attractor. No matter how you start in using this particular logistic growth model, you find yourself drawn toward this population value of 333. So suppose that for some reason the model were disrupted, the population suddenly dropped down to 100. Who knows what happens, okay? But then suppose that, again, the population growth model was operating as usual. What you discover is that the population would recover and it would tend again towards this limiting value of about 333. Okay, now I'm going to stick with logistic growth models, but I'm going to change the model in one way. I'm going to change the growth parameter, just as you did when you were examining this sort of thing with a spreadsheet. So now I've changed the growth parameter to 0.00315. That's the only thing I've changed. The carrying capacity is still 1,000. The initial population is still 500. But now we see a different sort of behavior in the population sequence. We see that very quickly the population sequence falls into this pattern of a higher value, a lower value, a higher value, a lower value, and it just oscillates between those two values forever. So how would we describe that in our newer language? Well, we would say now the attractor consists of 2 points. That is to say, we're drawn not towards a single population value, but towards a pattern of going between two certain population values, one a little bit less than 100 and another one in the low 500s, whatever they may be. The particular values aren't important. The important thing to note is that we can see that we're oscillating. We have this periodic 2 pattern. We have an attractor consisting of 2 points. Now, this is not a strange attractor, right? We don't use the word strange. If there's just 2 points, there's nothing very strange about that. We just find ourselves drawn into this pattern of oscillating between 2 values. And here again, I've changed the growth parameter. I haven't changed it very much. If you go back, you'll see it was 0.00315, and now it's 0.0035, which may seem like a tiny change. However, with this new choice of growth parameter, the logistic growth model now has an attractor consisting of, as you can see, 4 points. That is to say, we see that the population sequence goes through a pattern of 4 values. So one about 500, and then the highest possible value, which is close to 900, and then it drops down to something below 400, and then it comes back up to another high value, but not quite as high, slightly more than 800, and then it returns almost to 500 again. Okay, and it just goes in that same pattern, with period 4, forever. What we would say is now that the attractor consists of 4 points. All right, let's increase the growth parameter even more and ask ourselves, what could we expect to have happen? And amazingly, all of a sudden, when we reach a value about 0.0037, we see this rather chaotic and unpredictable pattern. Now, it's actually not totally unpredictable. What one can really understand about this, what deeper analysis will show, is that in fact there's a strange attractor. That is to say, it's not just one particular value that we're drawn towards, or 2, or even 4, but towards some very complicated fractal set, which is the strange attractor for this particular logistic growth model. So it's amazingly rich, this logistic growth model. It's a very simple formula, really. When you go back to it, let's go back again. There it is. Pn plus 1 equals r times c minus pn times pn. Amazingly, when you apply this using different values of r, you may see rather simple and predictable behavior, or something much more unpredictable. That is to say, the attractor could be very simple, a single point, or it could be several points, or it could be a fractal, as it is here. Now, one can understand this even further. I'm going to delve even deeper into this particular example by showing you what happens by trying lots of values for the growth parameter r and recording what you seem to see as the attractor. And here it is. Okay, so this is a very impressive diagram, I think. This is showing what's called the bifurcation diagram for this logistical growth model, or this logistic dynamic system. Now, the axis at the bottom, the horizontal axis, is recording the growth parameter. So starting at some low values, going up to higher values. And on the left, it's showing you, well, what numbers actually are in the attractor. So for small values of the growth parameter, there's just a single point attractor. It's slightly changing, right? So the actual value of the growth parameter controls exactly where the attracting point is located. But that's all that's happening there, right? As you slowly increase the growth parameter, you slowly change exactly what the single point attractor is. However, at some moment, suddenly the single point attractor bifurcates and it becomes a 2-point attractor. So now if you take values of the growth parameter somewhere to the right of the box that I've drawn, you'll see that a vertical line drawn there will cut into this picture twice, right? It'll hit it twice, and that's because those are the 2 attracting points, right? You're being attracted towards this cycle of period 2. If you go even further, the attractor changes from having 2 points to having 4 points, as we saw. And this is all part of what's called a period doubling cascade. That is to say, as you increase the growth parameter, you will see the attractor turn from a single point into 2 points, into 4 points, and then into 8 points. Now, you never looked at an example of this. I've never shown you an example of this. But as you can see, if you would very carefully pick the growth parameter, you could actually hit the picture 8 times, and that's because there is actually an 8-point attractor. And if you looked at the population sequence governed by this, you'd see that it was actually going through a periodic pattern of 8 units of time. But then if you go even further, as we have seen, there are growth parameters for which there is a strange attractor. Okay? This time when we take this vertical line and we hit the picture, we don't hit it in a single point or 2 points or 4 points or 8 points or in fact any finite number of points. What we do is we hit it in some kind of fractal set. Okay? So where that red vertical line is hitting that picture up above, it's hitting it in a fractal. And that fractal is slowly changing as we change the choice of growth parameter. Now, amazingly enough, you might think that's the end of the story. How could you go any further than being chaotic? But amazingly, you can push the growth parameter up to a value at which suddenly the attractor consists of just 3 points. And you've already seen that. If you go back and look at that spreadsheet that you used to look at logistic growth models back in an earlier part of the course, you'll see that there was a value of the growth parameter for which the attractor consisted of 3 points. That is to say, the population sequence was going through a pattern of 3 values periodically.